In this lecture, I'd like to describe how we can communicate the rate of a reaction so it's useful to others who are trying to use the reaction. We use rate laws to communicate information about the rate of a reaction. So we're going to walk through some of the components of these. So a rate law, in essence, is just an equation relating the concentration of reactants to the rate when the reverse reaction is negligible. So that kind of piece at the end there of that definition is really referring to, we're going to treat these as just all of our reactants will likely become products. And again, we'll talk more about these reversible reactions and equilibrium a little bit later in the quarter. And so right now we're going to just have to recognize that reactions proceed from reactants to products. And sometimes our products will form reactants as they collide, that there's a reverse reaction that occurs. And so we're going to work from the assumption that our reaction is just going to go from reactants to products, and that very few or none of the products reform reactants. Now, when we talk about mechanisms in this chapter, we're going to say, well, yeah, but some of them go back and forth. And so when we talk about a reversible reaction, we're saying that if our reactants can form products, our products can react and form reactants. So to build up this idea of a rate law, let's just start with the simpler version where our reactants become products. And the rate law is going to say, well, this change in concentration is going to relate to this rate. So the rate of a reaction is going to be, as we said, directly proportional to the concentration of each of our reactants. And so if we have a reaction where it's just reactant A forms products, it doesn't react with anything other than itself, we can write that rate law as the rate of the reaction. So here, oops. So that rate is the overall rate of the reaction times K, which is a rate constant, times the concentration of A, all to an exponent, which is going to be the order of the reaction. And this is going to be usually an integer. It can also be a fraction. But the ones we're going to look at in this class are going to be 0, first, and second order reactions. There's half reactions and 5/2 orders of reactions, but we can deal with that in a different class. And what that n value is doing, the order of the reaction, is it's really telling the reader or the person who's working with the reaction the dependence of the rate on that compound's concentration. So the rate of a reaction can be more or less dependent on different reactants and products. So let's look at what that n a little bit more in this order of the rate reaction. So here I've got orders 0 through 3 listed. So if something has an n equals 1, then we would say that it's first order with respect to, and this will always be with respect to one of the reactants or products. So the order of the reaction we can characterize as an overall order, but we also characterize the order for each of our reactants or products. And so this is for each reactant. And so if n equals 1, then that exponent is going to be a 1 after the concentration in our rate law. Now, it could be second order when n is 2. It can be third order with respect to the concentration of A if n equals 3. And it could be 0 order with respect to the concentration of A if n equals 0. When n equals 0 and our exponent is 0, then that means that our concentration to that exponent is always 1. And it's a way of saying that A, the concentration of A, doesn't affect the rate at all. We can have lots or we can have little, the rate will still be the same. So something that's 0 order with respect to the reactant is saying that that reactant doesn't impact its rate. And again, we can have fractions for n as well, like half or 3/4 or 5/2. So those also exist if you see them. So this is looking at, like, this is a rate law for something that's very simple where we have A going to a set of products. Most of our reactions are not that simple, though. A lot of them are going to have multiple reactants and multiple products. And so in this case, we're going to have a rate of a reaction that's going to include the dependence on all of the reactants. And so we'll focus on the reactants in our rate law. So we know that the rate of our reaction we can characterize by either the reactants or the products. And so that's that numeric value that says the speed of the reaction. And then this rate law is going to then describe the dependence based on the concentration. So we'll always have these same elements. We'll always have K, our reaction constant, which we'll have to calculate experimentally. We'll have the concentration of our reactants, and we'll also have the order for our reactants as well. So these will all be pieces of information that we need to use in our rate law. And what this will allow us to do is to say, hey, if I want to run this reaction, I'm going to start it with this 1.0 molar in A and 2.0 molar in B. What's my rate of my reaction going to look like? And so it's identifying that there's that rate that the reaction will take place is dependent on the concentrations you start with for your reaction when you make it. And so this is how we can kind of control the rate of a reaction too. One way you can increase the rate of the reaction is just by increasing the concentration of your reactants, because the more concentrated they are, the more they will collide. The more they collide, the more products will form at a faster rate. And so that's what these rate laws are really characterizing. Now, we like to characterize a reaction's overall rate. That overall rate for the order for the reaction, is going to be the sum of the exponents. And so here we go, sum of exponents. So in this case right here, it would be m plus n would equal the overall order of the reaction. And we can see, for simple ones, we can look at this graphically to represent this difference in orders. So this is going back to our simple example where we're just looking at one reactant A forming products. Now, if it's zero order, we will, this is looking at a change in like the concentration of A versus the rate. So if it's zero order with respect to A, then that means no matter what my concentration is, the rate is unaffected, or it just doesn't change depending on the concentration. If it's first order right here, then it's going to have a linear relationship. And so as I increase A, I'll see a similar increase in the rate. And second order right here, as I increase A, I won't see a linear relationship with the increase in rate. Instead, I'll see more of a logarithmic sort of relationship, where as I increase the concentration of A, I have a larger impact on the rate. And so as we see that order of the reaction increase from 0 to 1 to 2 to 3 to 4 to 5, we see that with a higher order, we have a higher dependence of the reaction rate on the concentration of that reactant.